Alright, we're going to be looking at kinematic graphs here today. And in terms of graphing here, there's several types of graphs that I want to show you. The first type is called a distance time graph. Sometimes this is referred to as a position time graph, but essentially, regardless of the shape here, I'll just draw something simple, maybe something going up here and then horizontal. Now, the shape of this graph here, okay, says that an object here is moving away from some reference point. So let's say that's 0 reference point, maybe he starts at 10, whatever numbers these are, they're moving away from some reference point. As time moves on, it's moving away in the positive direction, and at this point right here, okay, the object stops. It stops moving because it's staying at a constant distance away, or displacement. Okay, it's staying at a constant distance away, and time just keeps going. Now, something interesting about this graph, and when you're doing graphs, is several things. One is you'll never see a graph do this. In other words, it can't go back on itself. Okay, you'll never see graphs ever go back on themselves. So this will never take place in any of our graphs because you can't go back in time. Okay, that's impossible. Now, when we get to these ones here, just so you're aware here, in a distance time graph, the slope of this line does represent the velocity, and here's why. If I do rise, which would be distance, over the run, which would be time, well, that's d over t, and we know that that is velocity. Okay, you'll find out later that sometimes the area underneath the graph represents something. In this case, it means nothing, and the reason is because distance times time is no quantity that we're aware of in physics that's anything of meaning. Okay, so there's a distance time graph. A second type of graph is a velocity time graph. Now, velocity time graph, same thing. If I even draw the same type of shape here again, let's say going like this, what this states is that the object here is actually getting faster and faster and faster. Again, if I give these numbers on the side, 10, it's going 20 meters per second, 30 meters per second, 40 meters per second, and it gets faster and faster and faster. Yes, it's moving in the positive direction, but I guess you could say it's accelerating here. At this point, the object did not stop moving. In fact, if I gave this a number, it would be moving at, let's say, 50. My unit here is meters per second. It could be moving at 50 meters per second. Okay, it's moving at a constant rate, still in the positive direction. Now, when we look at this graph here, again, what does the slope and what does the area represent? Well, the slope of this graph, as you can probably already tell, is going to be acceleration. The reason being is because it's going to be a change in the velocity, let's say that's Vf and Vi, over time. Okay, so the slope will indicate the acceleration. What does the area represent? Well, if I take a piece of this right here, and I find the area underneath this graph, this area, okay, will represent the displacement. And the reason being is because it'll be velocity times time, which we already know as displacement. So the area will represent the displacement. The last type of graph here is something called an acceleration time. Again, say a graph like this, you probably won't be dealing with this very often in APB. And the reason being is because we have a changing acceleration here. Often this involves calculus to solve certain things. But again, just so you're aware here, the slope here would be a over t, or change in a over t. This means nothing to us. So the slope is nothing meaningful. Okay? But the area, on the other hand, would be a times time, which actually will indicate the velocity. Okay? In fact, it'll be the final velocity if there was no initial velocity. So the slope will indicate the area will indicate the velocity. Okay? The area will indicate the velocity. There's a little background on the three types of graphs you're going to get. What you need to know how to do is how to convert between these ones. And there are some ways to do this. In order to do this, I'm going to start off with something simple and just say like a DT graph. So here's a DT graph. This DT graph here, I'm going to just give it a shape. There's something similar. You know what, even the one I gave before, something like this. How would you convert from here to a VT graph? Well, if I drew a VT graph, based on this dt graph, what would it look like? First of all, it's important to know that it's always moving in the positive direction right here. How do I know that? Because it's a positive slope, and the slope indicates the velocity. Is it a changing slope? No. And because it's not changing, we must be moving at a constant positive velocity. What about here? Well, the object stopped moving. So in fact, instantaneously, the object would be somewhere down here on the axis. Okay, it stopped moving. There would be a VT. An AT graph from this, well, the slope of this line is 0. And so it is not accelerating there. Yes, it instantaneously accelerates. We're going to ignore that part. And here it doesn't accelerate again. Okay. Over here it kind of gets a little awkward because it's unbelievable that an object would change velocity in no time. But again, often the acceleration time graph, will be flat lines along the axis there because of the fact that we're not changing acceleration. How to move back and forth a little bit more with these graphs. You could get a graph that looks something like this. Suppose I gave you a dt graph now that curves. What does this mean? Well, obviously the slope is increasing, and the slope indicates the velocity. So if I did a VT graph based on this, I would have to have a changing velocity. Now, in fact, this one would probably look like this. Okay, maybe it started at 0, maybe not. Maybe it started at some number, but it's basically this. The velocity is increasing here at a constant rate. Again, we're not dealing with changing acceleration very often. The slope of this line, though, is staying constant, which means my acceleration, again, is a constant value. What would the acceleration be then? It could be some positive value because it's a positive slope, but it would